I want to summarize this lecture. In this lecture, we talk a lot about standing wave. And basically, I tell you that the superposition of the forward and partially refracted signal from the line will form a standing wave pattern on the transmission line. And this pattern repeats itself every half wavelength. And to understand the standing wave pattern and also how close the pattern is close to a standing wave, we define a figure called S. We call this the standing wave ratio. And if this ratio is big, then the standing wave pattern is very close to a standing wave. And this ratio is the maximum value of the voltage to the minimum value of the voltage, or the maximum value of the current to the minimum value of the current. And if you have 100% reflection, then you end up having S equal to infinite. So on the transmission line, the location of the maximum voltage will coincide with the minimum value of the current, or the minimum value of the voltage will match to the location of the maximum value of the current. And that is because of the energy conservation or power conservation on this line. And I also talk about open and short circuit, given the 100% reflection from the end of the transmission line low, and with 100% reflection, then the standing wave ratio is equal to infinite. And I also talk about the impedance transformation, because quite often that we need to know the reflection of a signal at a particular point on the line. So the impedance of this ZL is transformed into some other value given by this expression at this point. And then we remove this ZL, or cross down this ZL to have the open circuit or short circuit on the line. And then turn out that the input impedance for the open circuit or short circuit lines can give a value between minus infinite and plus infinite. Basically, any value of the impedance can be achieved by having this short circuit or open circuit transmission line. And then one important application of this short circuit and open circuit transmission line is to deduce the characteristic impedance of a transmission line. For example, if you multiply the open circuit input impedance with the short circuit input impedance, and then you take a square root of it, then you can determine the characteristic impedance of the transmission line. Or if you just divide these two values, put a minus sign here and take a square root of it, and the arctangent of this value will give you beta L. Because you know the length of the line in your experiment, so you can determine beta, the propagation constant of the line. So this is quite convenient if you want to sort of measure the characteristic impedance and the propagation constant of an unknown transmission line. And also we told you that a half wave line will transform the low impedance into itself, for the simple reason that you establish the standing wave patterns on this transmission line because of the forward and backward signals. And for a quarter wave transmission line, the input impedance is given by this value. And we have one important application for this results. If you have a transmission line with some reflection, you can append this transmission line with a quarter wavelength line, and you choose the characteristic impedance of this quarter wavelength line to be equal to the square root of the multiplication of this characteristic impedance and this ZL. Then you can remove the reflection of the signal on this line. And finally, we want to know everything about the transmission line, all the signals in the forward direction and backward direction. So we added the generated circuit to the transmission line. And this provide the last boundary condition for you to calculate the voltage in the forward direction. So this complete the analysis of the transmission line. This is about the key point I want to remind you before I close this lecture. Thank you for your attention.